So we've covered the kind of the 7 basic reactions that you guys are going to have for electrophilic aromatic substitution. And now we're going to kind of transition into kind of what happens when we already have one group on the benzene ring and how that impacts where that electrophile that you're adding is going to go. So we're going to talk about the synthesis of disubstituted benzene rings. Right, so having a group on your ring So having a group on your ring is going to impact where the second group is going to be added. There you go. So it's going to impact where the electrophile is going to go. So there are 2 groups or 2 types of groups we have to worry about for making benzene rings. And the first is an activating group. These increase the rate of electrophilic aromatic substitution and direct the electrophile ortho/para. So if there's an activating group on the ring, it's going to increase the rate of the reaction and it's going to direct that incoming electrophile ortho or para to itself. So these are normally electron donating groups. So EDG. So all those groups that we put on dienes from Diaz-Otto reactions, those are the groups that we're going to use here as our activating groups. So direct ortho para, never meta. Right? Your mom may have told you to never say never. I'm saying never. They never go meta. Only ortho para. Right? And then you have deactivating groups is the other group. Right? So this decreases the rate of electrophilic aromatic substitution. And directs meta. These are going to be electron withdrawing groups. Right, so again, all those groups that we put on dienophiles, those are going to be your deactivating groups. So these direct meta, never ortho para. So what are some examples of activating groups? So having an O minus, so like phenoxide, this is our most activating group. Then we have anilines. Then ethers. Then you have amides. So for these amides, you have the nitrogen is bonded to the aromatic ring, but there's an electron withdrawing group. There's a carbonyl bonded to that nitrogen. So it's not as activating as the aniline because the lone pairs are involved in resonance with that carbonyl. Then you have just boring like alkyl groups. So methyl, ethyl, propyl, those kind of things. Right? And your rate is going to increase as you become more activating. So if benzene is our kind of like fixed point, where it's like, all right, benzene's our baseline, that has a rate of, let's say, 1, our rate is going to increase. It's going to get faster relative to benzene as we work our way to the left. Right? Oops. These are also called ortho-para-directors. Right? So it's sometimes just like, oh, this is an ortho-para directing group. And that's pretty much synonymous with just being an activating group. So let's look at some examples here. So this is why I didn't give you any examples beforehand beyond just benzene, because I can't do any examples beyond benzene because there's all these rules you have to know. So you've got to do two things now, right? You've got to look at what your reagent is and determine what you're adding. And you have to look to see what's on the ring to determine where you're putting that thing that you're adding. Right? So you're like, okay, methoxy, that's just an ether. Right, that should be on the list, right? Yep, ether, right there. So that is going to direct ortho-para. And then Br2 and FeBr3 adds what to your ring? Bromine. Right, so we're going to put the bromine ortho or para. Typically, you're going to get a mixture of both ortho and para. So, like, usually in a written exam, I'd be like, yo, just pick your favorite for this, for your problem, right? I'm not going to have you draw both, just give me one. On these more multiple choicey exams, it'll be something where it's like, there might be three, say three wrong answers, obviously wrong answers, right? And then one that is just like just the para option. And you're like, okay, well, para is one of the products I can make from this, so that'll be the one I pick, right? So I don't necessarily have to put both for it to be the right answer. You can just pick, oh, there's just the Ortho product, I'll pick that. Now, you might be thinking, well, he put the bromine on the right-hand side. Why can't he put the bromine on the left-hand side? And these two Ortho positions, here and here, they're exactly the same. So it doesn't matter which carbon I put it on. At the end, I still end up with the same product, right? I get ortho bromo anisole, regardless of if it's on the left or the right-hand side. So in these simpler cases, the two ortho positions are exactly the same, so you don't have to worry about which ortho position you put it on. They're going to give you the same product regardless. So what am I going to add for this next one? You're going to remove the chlorine, and you're going to add that ketone, right? So we're going to end up with a ketone in our product. And again, it's going to be ortho or para. So again, these are interchanged, like these are both going to be your products. There's going to be some examples later on where we'll kind of specifically only get one or the other based on some other things going on in the structure. But for right now, just pick one, right? Ortho, para, both equally right. So then what do I add for the last one? So I add SO3H. Right, so you just need to make sure that you're doing both things. You're doing both the what am I adding, and then where is it going? So what am I going to add with HNO3 and H2SO4? So even though nobody's replying, I'm just giving you guys some time. I'm assuming you're saying it in your head. You feel good when I say it too. You're like, oh yeah, that was right. He doesn't need to know I know. It's all in my heart. So nitric acid, sulfuric acid, you add a nitro group. You add NO2, right? And again, methoxy directs orthopara. And there you go. Next reaction, I've got the bromine FeBr3, or the alkyl bromide and FeBr3. That's a Friedel-Crafts alkylation. So I'm just replacing the halogen with the aromatic ring. So I'm just adding isopropyl. And again, the nitrogen directs ortho para. The last one, I2 and nitric acid, adds iodide. Just adds an I to your compound. And again, the alkyl group directs ortho para. So an iodide here or an iodide here. So far, so good? All right. So the follow-up question is, why do these direct ortho para? Right? I could just say like they do and then like walk away. But probably want to know why. And the like short cop-out answer is resonance. But I should probably show you some examples as to why resonance makes this happen. So let's start with anisole. That's like the easiest one, right? I've got these lone pairs on my oxygen, right? So I can use those lone pairs to push electrons down and push them out on the ring. So then I get this negative charge on the ortho position, and I've got a negative charge beside a double bond, so I can draw another resonance structure. And I've got a negative charge beside a double bond, so I can draw a resonance structure again. Right, so I can draw three resonance structures by taking the electrons on my oxygen and pushing them down. And that makes gives a negative charge to the ortho and para positions. So what we can say with this methoxy group is kind of the same thing we did with dienes, right? We said for dienes that, you get these partially negatively charged carbons, and that we have the same thing here. So the ortho and para positions, when you have anisole, are slightly negative. We can kind of extend that to all of our electron donating groups that have lone pairs. This leaves out alkyl groups. Right? We can say, all right, for my electron donating groups, I'm going to say, hold on here, not alkyl groups. We'll go over them in a second. That in general, the ortho and para positions are going to be slightly negative. So if you're an electrophile that wants electrons, you're going to go to the carbon that has the most electrons, right? That's where you're most likely to react with, is where there are the most electrons. And so that's the ortho or the para position because they're slightly negative, right? The meta position is neutral, but the ortho and para position are negative, so that's where the electrophile is going to go. Right? And this also explains why activating groups are activating, right? The activating group is putting electrons into the ring. the ring is becoming more negative, so it's easier for that more negative ring to go add to a positive thing because it is better able to stabilize being positive because it's got all these extra electrons. So it can give away some electrons because it has extra electrons, right? So alkyl groups don't fit with this description or with this explanation because they don't have a lone pair, right? If you look at toluene, there's no lone pair on my carbon on my methyl group, right? So I can't draw resonance structures like I did. So I like to think about the intermediate that's going on the way to the product. So let's say we have our electrophile, and we add our electrophile to the ortho position. Right? I end up with a tertiary carbocation. Now if I add my electrophile to the, so I add my electrophile to the meta position, right? And I draw a resonance structure. So this is secondary. If I draw a resonance structure where I move these electrons over, I still get a secondary carbocation. So when I make my electrophile go on the meta position, I never have a resonance structure where I get to make the more stable tertiary carbocation. So this is adding the ortho, adding the meta. Now if I add para, same thing, electrophile. Right, I get a secondary carbocation here, but I can draw a resonance structure where I get a tertiary carbocation. Right, so when I add to the ortho or the para position, there's at least one resonance structure that gives me a more stable tertiary carbocation. Right? Oops. Well, adding the meta only gives me a secondary carbocation. So you can think, well, if I add ortho or para, I get a more stable intermediate, and that will help drive me to making the ortho or the para product. So that just a little bit of extra stability is going to help pick ortho and para over meta. So even though I don't have lone pairs, I can still kind of explain why the alkyl groups work. So far, so good. Now there's one group that kind of swings between being activating and being deactivating. So anilines go from activating to deactivating. Cannot do anything. Deactivating in the presence of strong acid. So our strong acids that we have to worry about are going to be nitric acid and sulfuric acid. So what happens here is we've got our aniline. Oops. And amines are basic. So we take our aniline, has an amine on it, and we mix it with strong acid. And what's going to happen is before there's a chance for our benzene ring to react with the electrophile, our aniline is going to become protonated. All right? So now this group is deactivating. So we never have a chance for our electrophile to react with just aniline, because as soon as the aniline gets around acid, it becomes protonated. Acid-base reactions are the fastest reactions in chemistry, so that reaction happens before the addition of our electrophile. So what we end up doing is we will make the product and the nitro group will end up on the meta position. So I should say this is deactivating and directs meta. See, this is our segue into deactivating groups. Very professional, very smooth. Throw a little crossfade in there, we're good. Deactivating groups now. So we're going to start with, I'm going to do this kind of in the reverse order. You'll see why in a second. We're going to start with benzene. Benzene's again our baseline, right? So everything to the right of benzene is going to be slower than benzene. So everything I have here that's going to the right, that is the right, will be slower than benzene. So, right. So we have like acids and esters. We have ketones and aldehydes. Nitriles. Sulfonic acids and sulfonate esters. Nitro groups. And then our ammoniums are R3, right, plus. So on this list, right, so this is our most deactivating. We'll actually give that some space. So as we get more deactivating, our rate decreases. So benzene is faster than benzoic acid at doing one of these reactions, which is faster than acetophenone, which is faster than benzonitrile, which is faster than the sulfonic acid, so on and so forth. Right. So the reason I did it this way is if you took the list of activating groups and then you took this list of deactivating groups and you stuck them together at benzene, you'd have like the complete spectrum. Right? On one side, you have your most activating groups and your fastest reactions. You'll go all the way over to benzene, and you'll go all the way over from there to your most deactivating group, your ammonium. So you can kind of stick those two like things together, those two charts together, and you see the whole spectrum. Right? Again, these direct meta, never ortho para. Right? The reason they slow the rate of reaction is they're removing electrons from the benzene ring. They remove electrons from the ring. So your ring is already short electrons because the substituent on it is taking electrons away from it. So the last thing it wants to do is then give electrons to something else. It already needs electrons. It doesn't want to give any of its electrons away. Right, so the stronger, the more deactivating the group, the more positive the benzene, the harder it is for that benzene to give up its electrons. The good news is that you only know like 7 reactions for these. So you're going to see them a lot as we do examples. So hopefully they all just end up being green in your head. The bad news is we end up kind of sticking a lot of rules on things. So it's like keeping all the rules straight, but like knowing your reaction should come second nature because hopefully we'll do enough examples that you're like, oh yeah, I know what that does. So here we're going to add bromine, right? So Br2 FeBr3 adds bromine. Nitro group directs meta. Only one product. Again, both meta groups are the same, so it doesn't matter which one you add to, right? So this metacarbon and this metacarbon are exactly the same, so it doesn't matter which one you pick. So here we're going to add tert-butyl, right? This is a Friedel-Crafts alkylation. Remove the halogen, just put the benzene in its place. And our ester directs meta. So we're just going to slap a tert-butyl group on here. Here we're going to add sulfonic acid, right? SO3, H2SO4 adds SO3H, and this goes meta. So what's nice about the deactivating groups is there's only ever one product, right? It's always just the meta product. So why do deactivating groups direct meta? Let us find out. And again, the cop-out answer is resonance. Right, so let's use acetophenone because that's an easy example. So now I can draw my resonance structure, but electrons are leaving the ring. Right, so I end up with a positive charge on my ortho position, but that positive charge is beside a double bond. So I can draw another resonance structure. I can move that. I have a positive charge on the para position. Again, is beside another double bond. So I can move it again. Right, so I can do the same kind of thing I did before. I can say, well, look, on my two ortho positions and my para position, I have a positive charge. So again, this is kind of like we did with dienophiles. I can say, hey, this electron withdrawing group is going to put a partial positive charge at the ortho and para positions. Right, and again, we can extend this out to pretty much all of our electron withdrawing groups. And say, hey, when I have an electron withdrawing group on my ring, my ortho and para positions are going to be slightly positive. So if you're an electrophile, right, which position are you going to react with? Are you going to react with a position that is already positive and lacking electrons? Or are you going to react with a position that is neutral, right? It's like, well, neutral's not negative, but it's better than positive, right? So I'm going to react with the most negative carbon I can, which, when there's an electron withdrawing group, is the metacarbon. So here, when you have a deactivating group, basically you give your electrophile bad choices and it picks the least bad place to go. When you have an activating group, right, you make three carbons negative. You give it three really good options to go add to, either ortho position or the para position. So it picks the best option for it. Where here it's like, oh man, all of these carbons are positive. I guess I'll go to the metacarbon. Fine, it's the least positive one. So your withdrawing group makes the whole ring overall is positive, right? Because it's pulled electrons out of it. So the electrophile doesn't really want to add to that ring anyway. The ring doesn't really want to add to it, but they eventually add, and the electrophile is like, fine, I'll go to this least positive place I can find. So I'll go to the meta position. Hokey dokey. So then there's one kind of like oddball group of groups, or oddball group of groups. There we go. Which are halides. And halides are hybrid groups, right? Meaning they're doing both things that deactivating groups do and activating groups do. So halides direct orthopara, but slow the rate of the reaction. So they do things that are like activating groups, right? They direct ortho para, but then they do things like deactivating groups, which is slow down the reaction, right? So they're kind of doing both things. They're like, I direct ortho para, but I make your reaction worse, right? So how does this work? So they donate electrons via resonance, right? But are electron withdrawing due to induction. So all induction means is by the sheer fact that halogens are electronegative, they pull electrons towards themselves. So they're pulling electrons towards themselves not through resonance, not where you can like draw a bond going to them, but because they're more negative than the atoms they're bonded to, so they pull electrons towards themselves. So through their single bond, they tug the electrons of that single bond towards them and pull electrons out of the ring. So when you have a halide, we'll use a generic X here, right? There's induction. You've got this negatively charged thing pulling electrons towards it. Right, so you're pulling the electrons out of the ring through the single bond. At the same time, so pull electrons out of the ring. At the same time, you have this ever so slight resonance structure where your halide is donating electrons to the aromatic ring through resonance. Great, and I get the exact same resonance structures I had with my normal electron donating groups. Plus. The difference is halides hate being positive, right? Their whole shtick is I'm electronegative, I want electrons, right? The last thing they want to do is give electrons away to be and become positive, right? So even though this resonance structure can happen, right, it might be a situation where it's like 99% of the time the electrons are hanging out on the halide not being shared, and then just 1% of the time those electrons are down in the ring doing stuff. These aren't real numbers, just get your head around it, right? So it's a very small contribution to the resonance of the ring is the halide giving electrons because the halide doesn't want to be positive. But that little bit of resonance that it does give, that little bit of electron density, you do end up with your halide making these carbons really teeny tiny, teeny weeny negative charges, right? In that slight difference, just that little bit more extra negative charge on the ortho and para position is enough to make it so when there's an electrophile, the electrophile is like, oh, ortho and para, those are slightly more negative than the meta position. Fine, cool. I'm going to add to the ortho and the para position. So even though it's not a big contributor, right, because you have to make your halide positive, there's enough of a contribution that the electrophile notices that the ortho and para positions are more negative than the meta position, so they will go there. So the halide's doing kind of like, it's working against itself. It's pulling electrons out of the ring through induction and then just gives a little bit back through resonance, just enough to make the ortho and para positions negative and select for ortho para over meta. Right? So it's, what are we adding? Where is it going? So chlorides, though they're weird, they direct ortho para. So I know my product's going to be ortho para, and I know that I2 in nitric acid adds an iodine. So there you go. Br2, FeBr3, that adds a bromine. Nitrogen, right? We're not in the presence of a strong acid, so nitrogen is going to direct ortho para. Bromine. And then last one, this is going to add SO3H, and CN is electron withdrawing. It's a deactivating group, so it's going to direct meta. So far, so good. So on Wednesday, we're going to do what happens when you have two groups on the benzene ring and you want to put a third. How do you decide where that third group goes? And that'll be that. And we'll probably get through that and then do some more fun stuff. So I will see you guys in the next class.